Here is the lecture notes for section 7.1. Chapter 7 involves talking about sampling distributions, an idea that is going to be fundamental to our talk about statistical inference. Statistical inference is the major theme for the entire last part of the class. We're going to be talking about this again and again and again. But here's the basic idea that we are always trying to find out information about a population. And numbers that define or summarize a population are called parameters. But getting information from a population is really, really hard. Populations are really, really large. Getting everyone in a population is really, really hard. So instead of dealing with a population, we're going to take a subset of a population called a sample. And if we do a good job of using randomness, we will get a representative sample. And if we get a representative sample, we can summarize that random sample. And when we use a number to summarize a random sample, we get something called a statistic. And we hope that that statistic gives us insight about what's going on in the population, that we could infer the result of the sample to the population itself. And that process is called statistical inference. Now, in this section, we're going to define more readily the idea of a parameter and statistic. We're going to talk about what it means to be a sampling distribution. We are going to distinguish between a population distribution, a sampling distribution, and what we refer to as the distribution of the sample data. We'll talk about this idea of a statistic being unbiased, and then we'll talk about how sample size has an effect on the variability of our statistic, our estimator for a population. So let's dive in for first with some definition. It's in a box, so it must be important. A parameter is a number that describes some characteristic of a population. In statistical practice, the value of the parameter is usually not known. Why? Because it's really hard to get information from an entire population, even if the population is relatively small. A statistic, on the other hand, is a number that describes a characteristic of a sample. The value of the statistic can be computed directly from sample data. And those numbers are easier to get. So reminder that parameter starts with a P, and that's information that comes from a population. Statistic starts with an S, and that's numbers that come from a sample. Now, typically what we have is we have different symbols to represent the different ideas. So, for example, we'll use the Greek letter mu to represent the mean of a population, but we'll use X bar to represent the mean of a sample. We'll use the letter P to represent a proportion that comes from a population, but we'll use P hat to represent a proportion that comes from a sample. It's important for us to be able to distinguish samples from populations. So let's go through this check for understanding to get those ideas across. It says identify the population, the parameter, the sample, and the statistic for the following settings. A pediatrician wants to know the 75th percentile for the distribution of heights of 10-year-old boys. So she takes a sample of 50 patients and calculates that the Q3 score is 56 inches. What's our population in this case? Well, the population, the thing that's hard to get at, would be all 10-year-old boys. And what's the parameter? Well, the parameter would be the Q3 score for heights from all 10-year-old boys. Now, that'd be a very difficult thing to get a hold of. So because that's hard to get a hold of, let's talk about the sampling that she did. What was the sample? Well, it was the 50 patients Now you can argue whether that's a good sample or not, but the sample was the 50 patients that were 10-year-old boys. And what was the statistic? Well, the statistic was that Q3 score that she got, 56 inches. The Q score from those 50 10-year-olds. Item number two, the Pew Research Center asked 1,102 12 to 17-year-olds in the United States if they had a cell phone. Of the respondents, 71 said yes. So what's our population? What's that group that's difficult to get to? Well, that would be all 12 to 17-year-olds. Okay? And what's the parameter? Well, the parameter would be the proportion of all of the 12 to 17-year-olds that have a cell phone. Obviously, this is old data, right? But what did Pew do? Did they talk to all of the 12 to 17-year-olds? No, they did a sample. So what's the sample? It'd be the 1,102 12 to 17-year-olds questioned, the respondents. And what was the statistic? What was the number that summarized that sample? That'd be the 71% who said yes. So 71% of the sample who said yes. All right. In this next exercise, questions 3 and 4, there are bold-faced numbers. Are they parameters or are they statistics? On Tuesday, the bottles of Arizona iced tea filled at the plant were supposed to contain 20 ounces. Quality control chooses 50 bottles at random from the production. These bottles contained an average of 19.6 ounces. I say that the average was supposed to be 20, that this number is a parameter because it's of all of the bottles. I say that a statistic in this situation is 19.6 ounces, and it's the X bar. OZ. There's our label there. On a New York to Denver flight, 8% of the 125 passengers were selected for random security screening before boarding. According to the TSA, 10% of passengers are chosen for random screening. Well, the parameter is of all. So our parameter, P, is that 10%, 0.1. The statistic coming from a subset, coming from a sample, that's 8%. Okay, and we use different symbols, P hat for sample proportion, P for population proportion. All right. So what happens when we sample? Well, when we sample, the basic idea is that every single sample has a bit of randomness in it. And so from each sample, we get different values for our statistic. Because each sample are random, each sample statistic will vary. Okay. And since a statistic is a number, and because it's random, we don't know what's going to come out from sample to sample. The statistics are random variables. And everything that we learned in chapter 6 about random variables comes to apply here. Now, what do we do with random variables? We tend to look at the distribution of random variables and look at their shape, at their center, and at their spread. So let's think about doing that for our statistics. Now, here's an activity. I'm going to pretend as if we did the activity with multiple students. The idea is that we were to have a bag full of poker chips. And in that bag of poker chips, some of them, 100 of them, 200 total chips, 200 of them were the same color. So let's call them red. All right. And you would, from person to person, you would grab in and grab out 20 chips, and then you would do a calculation. You would find out what proportion of your sample had 20 chips. Or sorry, of the 20 chips were red. Now, again, because I can't do this, I can't do this with you in a recorded lecture. I'm going to pretend that we are doing it. I have in my calculator here a list, and this list has 100 ones, which represent the 100 red chips, and it has 100 zeros representing some other color. Let's call it green, right? And we can look at the distribution of that population. 100 of these little dots are lined up at 0, and 100 of these little dots are lined up at 1 to represent all those red chips. Now, what can we do to simulate drawing from that bag? Well, we could use something called a command called random sample. Now, in a random sample, we say, where are we getting our sample from? We're getting it from that thing called population. Say, how many chips are we drawing? We can say 20. And lastly, do we want to draw without replacement? Well, if we were doing this live, we would be drawing it without replacement, meaning I wouldn't put my hand in, get one chip, put it back in, draw again, put it back in, so on and so forth. So if I hit the enter key right now, there is 20 zeros and ones that were randomly drawn from that list of red and green chips. Okay, now I'm just going to do a couple of extra things here. That is a random draw. If I hit another one, I get a different random draw. But I'm not interested in what the chips are. I'm interested in what proportion of them are red. So if I type in the word sum and then feed into it a random sample, this adds up all the ones that were in that list. I get 7. Great, 7. But 7 is not a proportion. 7 out of 20 is a proportion. So I'm going to go back here and we're going to say, well, how about if I take that random sample and then divide it by 20? Oh, that is a random sample. And that is a sample proportion, a p-hat value. 0.3 is one of those values, right? If I hit enter again, new random sample, and new p-hat value. Oh, 0.45. So I've just done 2 samples, and indeed we had sampling variability. The p-hat value varied from sample to sample. let's do a quick thing and do some sampling. 2, 3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. And let me put my 0.3 in there and my 0.45, and let's just do some sampling. Oh, 0.5. There's another handful of chips. Half of them were red. Another handful of chips. That one had 35%. 0.7, 0.45 again, 0.65. Let's see if I can get 20 of these on here. 0.5, 0.5, 0.45 again. What do we expect coming out of here? What do we expect? Do we expect them to be much different than 50%? Is it surprising that we're getting a lot of these numbers around 50%? I don't think so. I think this is kind of what we expected. I am getting more 45s and less 55s than I expected. Can I get a 55 in here? 4.5. Okay, that's enough for right now. Okay, so what do we see? We see variability. We see a shape, perhaps. Perhaps we might say that this is looking normal-ish, maybe approximately normal. Certainly got a hump in the middle and kind of edges on the edge. Do we see a center? That center seems to be around. The mean maybe is around 0.5, maybe. And spread. Spread. Maybe we could use range for this because I don't want to do a standard deviation. Largest one was 0.7, smallest one was 0.3. Okay, so our range was 0.4. Okay, anything unusual? Do we think that's an outlier? Do we think 0.3 is an outlier? Hard to say right now. Okay, let's go on and see how what we just did fits into the big picture. And the big thing that I want to talk about is this thing called a sampling distribution. Okay, you saw me get a bunch of p-hat values, right? And start making a distribution out of them. A sampling distribution has a very particular definition. Sampling distribution of a statistic is the distribution of the values taken on by the statistic from all possible samples of the same size from the same population. Okay? And it says, in practice, it is difficult to take all possible samples of n to look at that sampling distribution. How hard? How many different samples of size 20 are there coming from this particular sample? Well, if I use our friend NCR, and say, hey, we got a sample size of 200. How many different ways are there to choose 20 things? Well, that's how many different ways there are to get 20, a sample size of 20 from a population of size 200. Okay, 1.6 times 10 to the 27th. Okay, that's a lot. That's a lot of different things. So us showing what the sampling distribution is like is really, really hard. So what we're going to do instead is say, what if we were to do a lot of samples? Let's say, how about we do 500 samples, getting the p-hat value from each sample, and then perhaps we can take a look and look at that. They did this for us. There's a bunch of dots here. Each of these dots represents one p-hat value, right? Is it a sampling distribution? Is it a sampling distribution of p-hat? Answer is no. This is not sampling distribution because this is not all possible samples, but it is a reasonable estimate. And what do we see in this regional estimate? How about its shape? Well, it looks approximately normal to me. How about its center? Does the center look, does the mean of that distribution look like it's 0.5? Sure does to me. And then what about its spread? What about its spread? Again, we might look at the range here. The range, oh, 0.8 to 0.15. That's a pretty big range. That looks like it's 0.65 is the range. Maybe we can do a better idea, a better thing here. Ready? What if I go to this calculator and say, I want 500 samples of size 20. And I'm going to put them into a list, which I'm going to call P hat, or I should say P hats, because there are multiple P hat values that are going to fill in this list. So I did a draw, got a 45, I did another draw, got a 0.55, got 0.25, 0.45, all that. Let's take a look at that distribution. Go ahead, look at all those P hats. Does that look similar to what we have here? It sure does. Okay. Do we have could we calculate the mean of this? Sure, we could go back to a calculator page and I could ask, hey, what's the mean of those P hats? Oh, really close to 0.5. Not surprising. I can also run one bar statistics. Uh, Statistics, calculation, one bar, and I could say, please find out all this information out for me from those p hats. Okay. Oh, and we get a standard deviation. That standard deviation is 0.09982. Okay, that's interesting. Maybe that something we can explore later. Okay. Other thing, other outliers. Did we get any outliers here? Well, if I take a look at this um, as a box plot, did I get some outliers? Oh, yeah, I did. Okay. Didn't do the calculation to prove that they're outliers, but those are unusuals. Okay. Let's go back to the dot plot of this. All right. So what can we do? What can we say about this estimated sampling distribution? What use is it? All right. So suppose your teacher prepares the bag and claims that half of them are red. Classmate then takes a simple random sample of chips. 17 of them are in his sample are red. 17. That's a p hat value of 17 over 20. That's a p hat value of 0.85. Okay. Interesting. Oh, wait. When we looked at the sampling distribution, how often did 0.85 come up, at least in this one? Oh, never. Hmm. That seems very fishy then, that there was a sample with 0.85, and in 500 simulations, we never got a 0.85. Wait, what about in our calculator? How often did we get a 0.85? Oh, looking here, never. Okay. So what's our takeaway from this? Because there were never a sample that produced a p-hat value of 0.85, we suspect the teacher's bag not having a population proportion of 0.5. We're suspicious because of the low probability. Now, we got some vocabulary here. We have lots of different things that are called distributions in this scenario. We have a population distribution, the distribution of the population looking at it as a whole. 100 blue, 100 red. Okay. Now, when we take a sample, we get what's referred to as a distribution of sample data. Oh, in this particular scenario, 8 of them were red, so the p-hat value, the sample proportion is 0.4. Here's a different sample, and these are graphs of sample data. Now, if we take this p-hat and this p-hat and this p-hat and many other p-hats and then put it on a graph, this is a sampling distribution or at least an estimate of a sampling distribution. So 3 different kinds of distributions. We need to know the difference between those 3. All right. Now, let's check for understanding. Okay. Says Mars Incorporated says that a mix of colors in M&M milk chocolate candies is 24% blue, 20% orange, 16% green, 14% yellow, and 13% brown. Assume that the company's claim is true. We want to examine the proportion of orange M&M candies in repeated samples of 50 candies. Okay. Which of the graph could be the approximate sampling distribution? Could this one be? Now, this one is a population distribution because it has all of the different colors. Could this be a sampling distribution? Well, it's got a bunch of p-hats in it. If it's got a bunch of p-hats in it, that could be a sampling distribution. Oh, wait, this is also p-hats. Oh, wait. If we were sampling from a population that was 20% orange, wouldn't we expect the sample proportions to all be around 0.2? So this could be an estimated sampling distribution of orange candies. This, some sort of sampling distribution, but not of orange, because we expect that the middle would be around 0.2, and it's not. All right. Let's go on. Describing sampling distributions. We have a word here that we're going to use repeatedly. And I want to be careful because this word is unbiased and it's different from the normal use of the word unbiased. It says, how trustworthy is a statistic as an estimator of a parameter? Because what we want to look at a sample and try to get insight about a population. Okay. In this example, we did 20, size 20, and we got an estimate of a sampling distribution. And we note again that the center of that sampling distribution or estimated sampling distribution is around 0.5, which was the population proportion itself. When this happens, when the mean of the sampling distribution is the same as the population parameter it's trying to estimate, we say the statistic is an unbiased estimator. And that's a good thing. It means that we can look at the statistic and we feel like we've got insight about what's going on at the population level. Now, that unbiased stuff is talking about the mean. What about spread? Well, here's an idea. I would prefer to have lower variability than higher variability. I would prefer that all those little things that were estimates to the parameter, I would like them to be close to the actual real answer. Now, we saw in that in this distribution, while the distribution was the population distribution was about 0.5, that down here, we got 0.2. That's really pretty far away. That's a pretty big difference between there's a lot of spread in this. Okay. Let's take this for another example. Let's say it says television executives who advertise on TV are interested in how many viewers watch a particular show. According to Nielsen ratings, Survivor was one of the most watched television show during every week it aired. Suppose the true proportion of US adults who watched the show was 0.37. Now, if we take repeated samples of size 100 from a population where the proportion of viewers that watched for Survivor was 0.37, we can get a distribution of all those different p-hats. Now, look at the variability there. It goes all the way down to 22%, all the way up to 52%. Even if they do everything right, sometimes they said, hey, looks like 52% of the population was watching the show, when in fact, 37% was watching the show. This is from a sample size of 100. If we change our sample size to 1,000, what do you see about the variability in there? Wow, we barely got down into 31s, barely got up into the 43s. The vast majority of those different p-hat samples from the simulation were really close to 0.37. We prefer low variability. We prefer our answers to be closer to the real answers. And we say that the key to doing that is having larger sample sizes. The variability of a statistic is described by the spread of the sampling distribution. The spread is determined primarily by the size of the random sample. Larger samples give smaller spread. And that makes sense. The more information you have, the more likely you're making a good guess about this thing that you don't know. The spread of the sampling distribution does not depend on the size of the population, as long as we meet that independent enough condition, the 10% condition. So it doesn't matter the size of the population. What matters is the size of the sample. Let's check for understanding. The histogram on the left shows the intervals in minutes between eruptions of Old Faithful in Yellowstone Park for all 222 recorded eruptions in a particular month. By the way, just to note this, this is a population distribution. All right. Now, for this population, the median was 75. Okay, so that's a median from the population. Now, we use software to take 500 simple random samples of size 10 from that population and then calculate from that 10 the median of each of those samples. We took those medians and made a graph out of them, and they are there. Okay, is the sample median an unbiased estimator of the population median? Well, the population median, as described, was 75. The mean of the 500 sample medians, so the median of 500 samples was 73.5. Are those the same number? No. Are they close to the same number? Not really. Conclusion: sample median is not an unbiased estimator of population median because the mean of the distribution of medians does not equal the population median. Not every statistic is unbiased. Not to say that we do something wrong, it's just that it doesn't do what we want it to do. Second question. Suppose we've taken samples of size 20 instead of 10. Would the spread be larger, smaller, or the same? Larger samples give or make sampling distributions have lower variability. Therefore, the spread with sample size 20 has less spread. There we go. Item number 3. Describe the shape of the sampling distribution. Well, here's the sampling distribution, or at least the estimate of the sampling distribution. That looks to me like the shape is skew left. Now, explain what this means about overestimating or underestimating the population median. Well, we know in skew left distributions, the mean is pulled toward the tail to the left. Therefore, it is not surprising that the mean of sample medians is underestimating. All right. Let's talk about our goals. So we know that we're doing these sampling. We know that we're trying to estimate what's going on at the population level. We claim bias is a bad thing. We would like to be unbiased. We claim that what we want is low variability. Low variability meaning less spread from our statistics so that they're closer to the real answer. Metaphor here is that between high bias or low bias, high variability or low variability, we would like no bias and no variability or low variability. We would like our estimates to be right in the center of the thing that we're trying to estimate. Okay? If we have a second choice, this is our first choice. If we have a second choice, our second choice is to have low bias but higher variability. We would prefer to be around the right answer, but variable. We don't want that. Low variability and high bias, That's no good for us. We're going to give a very, very confident answer, and that answer is going to be wrong. Okay. So how do we achieve low bias? Well, we choose variables that are unbiased, and we do things like make sure that we use good random sampling techniques. How do we get low variability? We do so by having large sample sizes. All right. So watch out for the fact that the sampling distributions has many shapes. We would prefer it to be nice and normal, and we'll find out under what circumstances that occurs. But finishing off, in World War II, the Allies worked really, really hard to estimate the number of tanks that the Germans were producing by looking at serial numbers on the tanks. Now, when we captured a tank, we could say that those tanks captured represented a random sample of all the population of all German tanks. Based on that, we could then try to estimate, well, how many German tanks are there? There's a couple different techniques for doing this. And in the activity described in the book, the kids used 4 different estimates after pulling a sample of tanks out of a bag. And then those techniques were tried again and again and again and created these sampling distributions. Of the 4 that the students do, which one is the best? Well, we want, again, low bias, and we'd like low variability. Okay. Of the techniques that we saw there, are any of these biased? Where the mean of the distribution is different than the target mean for the simulation, which was 342. And I could say, maybe this one's got a little bias. Maybe its mean is not the same as the population mean. I think the other of these 3 are all low bias, right? And of those low bias, that's my first round, which of them has the smallest variability? I'm thinking rough estimate would be that max min has the lowest variability of the 4 low bias estimates. Now, that's one way to do it. What's another way of doing it? Well, partition is the one that it was actually used in World War II. And as you can see, it has low bias. Sorry, the major clumps here is pulled toward the tail. This ends up being really close to the true mean. And of all those techniques, it has the lowest variability. So as we conclude this lecture from 7.1, we got to remember that parameters are numbers that describe populations, and we often use statistics, a number from a sample, to estimate those parameters. Population distribution describes all the values of the variable from a population. A sampling distribution, though, takes repeated samples from that population of the same size and then looks at the different values that the statistic takes on from those different samples. Some statistics are unbiased, meaning that the mean of their sampling distribution is the same as the parameter that we'd be trying to estimate. Variability happens when we do this kind of sampling or looking at these sampling distributions. Larger samples give smaller spread, and we like smaller spread. Okay. When trying to estimate a parameter, we choose a statistic with little or no bias. And remember, the shape of that sampling distribution can affect the quality or the bias in that situation. I hope this was helpful.